Hello and welcome to a new calculus part. Today we're going to be talking about function approximations, and specifically we're going to try to approximate the function f of x equals the natural log of x plus 1. So what do I mean by function approximation? Well, let's say that we have some kind of problem and this natural log is really causing us trouble, like the equation becomes really hard to solve or something like that. And what we'd actually want is some kind of polynomial. So remember, a polynomial is something with x squared or 3x cubed or something like that. And if we were to have a polynomial instead of this natural log, then it becomes easier to differentiate, it becomes easier to integrate. Just all around, polynomials are more well behaved, right? So if we could find a polynomial that approximates this natural log around some point, then, well, that would solve our issues. Obviously it's not a perfect match, but because that's what an approximation means. But for like in engineering or something, not a perfect match is fine. If it's good enough, then it works. If it's a polynomial, it's easier to work with, and that just solves a lot of problems, right? So let's see if we can find a polynomial approximation for the natural log. Well, a good place to start is just to graph the function a little bit. So this is our y and x axis to see what our goal is. Alright, so the function f of x kind of goes like this through the origin, like that, and then it goes down, at -1 in a vertical asymptote. Alright, so let's say the problem specifies that we want to find an approximation near x equals 0. So let me just write it down, near x equals 0. Alright, so what can we say? Well, first of all, we can just outline a very general polynomial to see what we're working with. So a very general polynomial would be something like c0 for just a constant, then c1 times x plus c2 times x squared plus c3 times x cubed, on and on, something like that. And then you can cap it off when you have enough precision, right? Alright, so let's think about it. So what do we want the approximation to have? Well, first of all, if it's going to be any good at all, then the function should also equal 0 at 0, right? It should have the same value around the point that we want to approximate. And to do that, we can actually see what does our function equal at 0. Well, that's going to be ln of 1, which is just going to be 0. So we want our polynomial when we enter 0 to also equal 0. Let's see how we can do that. Well, if we enter 0, then all terms with an x, they all become 0, which leaves us with just c0, which means that c0 is just equal to 0. So we've already found one of our constants here, if you will. And now our polynomial goes just c1x plus c2x squared, on and on like that. Alright, so now we've made sure that the polynomial equals 0 because the function also equals 0 at that point. So now what we can say is we can actually say, well, any function, something like this, does also equal 0 around x equals 0, but we want something that is a little bit more tangent to our graph, right? It kind of has to have the same shape. So we want something that also has the same derivative at x equals 0. Something like a tangent line would already be better, right? So what we can say about that, so we want them to have matching derivatives at x equals 0. So we want our polynomial, the derivative of a polynomial, to have the same derivative as our function when evaluated at 0. So let's first of all find the derivatives of, first of all, f of x. That's going to be natural log, so we just have to divide that, and by the inside that becomes that. And then we can fill in 0 that's going to be just 1, like that. Alright, and so now we have to find the derivative of our polynomial. When we look at this, we can say that, well, this x just cancels out, just leaves us with c1, and then this 2 is going to jump down in front of the c2, leave us just with an x, and then if I go one term further, it's going to be 3 times c3 x squared, and then another is going to be like that, and it just goes on and on like that. Alright, so that's the derivative of our polynomial. And so now, and we can now just evaluate it at 0, right? Because that's what we want. So we want the derivative of our polynomial to equal the derivative of our function, which is just 1. We found that earlier, like that. Alright, so let's see. So let's evaluate the derivative of the polynomial at 0. Again, just like we saw before, every term with an x will just group, that will cancel out to 0, which just leaves us with c1, which means that c1 is going to equal 1, which look at that. So now we've already have a little bit of a better approximation. We can now say that our polynomial is x plus c2 x squared plus c3 x cubed, something like that. And I'll do just one more term so you get the gist of it. And then we'll see how well it approximates in Desmos. We'll see how well it approximates, right? Alright, so just one more term, c2. And for this, we'll make sure that the second derivatives match. So we want to have that the second derivative evaluated at our point 0 is going to be the same in the function and the polynomial. Alright, so first of all, the function, we'll differentiate that. That's going to be negative 1 divided by 1 plus x squared. Alright, and evaluating that at 0 gives 1 divided by 2. Is that correct? That's not correct. That's going to be just negative 1. Almost a little bit of an error. No, it's going to be negative 1. Alright, so now we just differentiate the derivative of the polynomial to get its second derivative. So the second derivative is going to be the derivative of this. That c1 is just going to cancel because it doesn't have an x, and then this, I'll just copy this, leave the x out, then a 2 jumps forward here, c3 x plus, it's going to be 12 c4 x squared, on and on like that. And again, if we enter 0, all our x's cancel, this becomes 0, and we're just left with 2c2. And then we have to make sure that they match, so 2c2 is going to be equal to negative 1, which gives us c2 is equal to negative a half. Alright, so now we have 3 terms in our polynomial. So our polynomial is now going to be, and now I'm just going to leave out the x cubed terms and higher terms, so we can see what it becomes. Alright, so polynomial will be, first of all, c0, that's just equal to 0, so we can leave that out. And then c1, that was equal to 1, there we go, equal to 1, so we have 1 times x, and then c2 is going to be negative a half x squared. So our function is x minus negative a half x squared. That's our function. Alright, and we have that to approximate the natural log of x plus 1 around x equals 0. Right, so let's see how those square up. I've already plotted them here. So in red you see the natural log function, and in blue is the polynomial. And you can see that around 0 they match pretty well. So it's actually quite a good approximation if you're just working with values around 0. Obviously, if you were working with values around, let's say, x equals 2, then you wouldn't constantly be inserting 0, you'd be inserting 2, right? Because that's a little bit, well, it's bad. That's more useful, right? I mean, in principle, you could keep going and add higher and higher terms, and then you would eventually get quite a good approximation at 2, but then you'd kind of be losing the point of doing the polynomials, right? So, to give a little bit of context, these polynomials are what's called Taylor series or Taylor expansions, and if they're around 0, you might call them Maclaurin expansions, I believe they're called. But they are a way to approximate any function really that's differentiable around a certain x value. And you can also do this, for example, for e to the x. Then you'll find you can keep going forever, right? Because you can keep differentiating and you'll find more and more terms. And you can do this for sine of x, like that. And well, that's basically what Taylor series are. They're a way to approximate functions, and sometimes they can actually equal the function. So if you keep going forever with e to the x, you can actually find a certain definition for e to the x that I believe I talked about in my complex numbers video, like that. So that's going to be something like this. You can eventually derive this function from the way Taylor series are defined, basically. And because you'll keep going forever, eventually this polynomial, because look, this is polynomial, I'm just raising x to some power n, it actually equals e to the x. So that's kind of a fun side thing. But that wraps it up, I think. So thank you for watching, and I'll see you in the next part. Bye bye.